Complete number 3, the setup is a over x plus 2 plus b over x minus 3 because we have to factor this denominator. It's x plus 2x minus 3. What this fraction needs is the x minus 3, and what this fraction needs is the x plus 2. So we'll put x minus 3 next to the a and x plus 2 next to the b. We're going to bring down the x plus 7, and we're now setting all the numerators equal to each other. So I'm showing you one way of solving this, and then I'll show you another way. So here we look at this factor, and we say if I plug in 3 for x, it'll give me 0. So we're going to let x equals 3. So we'll plug in 3 everywhere there is an x. That's in red. 3 plus 7 is 10. So we have 10, and then equals, and then 3 minus 3 is 0, so this a term goes away, and then 3 plus 2 is 5, so we will have 5b, and when you divide, you get b is equal to 2. Okay, and then in this method, here, if you look at this factor that I'm circling, x plus 2, we would have negative 2 would give you 0, so negative 2 plus 2 gives you 0, so these would cancel. And then we have negative 2 and negative 3 is negative 5. So we have over here, negative 2 plus 7 is 5, set equal to negative 5a. And when you divide, you get a is equal to negative 1. So you will go back up here and replace a with negative 1 and b with 2 as your final answer. Here's another method for solving. Okay, so what you can do is you could set it up the same, but now if you distribute a and distribute b, you end up with ax minus 3a plus bx plus 2b. I'm going to group the x terms together, and then these are considered the constants because they don't have an x. I'll factor out an x for these two, so we have a plus b, and then I'll just put these in parentheses. So what I'm going to do is that the x plus 7 I'll write underneath, so there's not a 0 in front of the x, there's actually a 1. So if we put a 1 in front of the x, we can now write this equation, a plus b equals 1, and negative 3a plus 2b equals 7. So that is this equation. So what we're working with now is a system of equations that we have to solve. As you can see, this ends up being a lot more work than this method I just showed you. Okay, but this is a method you would have to use for repeat linear or quadratic factors. So if we were to continue to solve this system, I would multiply the top equation by 3, and you can see why. You have 3a plus 3b equals 3. If you rewrite the bottom equation underneath, what will cancel out is the a's, and what do we have left? We have 5b equal to 10, and when you divide by 5, you get 2. So we have our b term. And which is the easiest equation to use to solve for a? I would say this one, the a plus b equals 1. So if we go to a plus b equals 1, we plug in 2 for b. We will then get a is equal to negative 1 when you subtract 2. And then your final answer is going to be negative 1 over x plus 2 over x minus 3. So just a reminder, again, why this is a setup for this question. X minus 1 is a linear factor. It's being squared, which means it's being repeated. So this is technically x minus 1 times x minus 1. Okay, so you put it as a single, and then you put it as a double. And then the x plus 2 goes here. These are all linear denominators. This 2 just means because it's being doubled. So you have constant numerators. Okay. For question 5, if you factor the denominator, you could take out an x from each term, and we have x, and then we have x squared plus 4. x plus square plus 4 is not factorable, so that stays a quadratic. So that becomes bx plus c up top, because that's linear, and this is quadratic. This is linear, so this is constant. Okay? And the last one, this is a quadratic that's being repeated. So you're going to write it as a single, and then you're going to write it as a double. Okay? And then the ax plus b needs an extra x squared plus 2, so you're going to have to put that next to the ax plus b. Okay? This doesn't need anything to be changed since the denominator is exactly what you have. You need to go to section 7.4 in the textbook and look over the 4 examples that are laid out in the textbook, as well as go on to YouTube and just type in partial fraction decomposition. You could type in linear factors, repeated linear factors, quadratic factors, repeated quadratic factors, and see examples. Alright, I want to go over this example that I gave you in class. So you start by looking at these 3 equations that we need to graph. We could look at the x and y intercepts, so if you cover up one and solve for the other. So for this one, x is 2, 2 times 6 is 12, and 3 times 4 is 12. 2 and 4 are on the grid given to us, so we could connect these with the red line. If you cover up this and divide by 2, you get x is equal to 5, but then when you cover this one up and you divide, you end up with y is equal to 10 over 3, which is negative 3 1/3, which is not on the graph. So the only point we could actually plot is the x-intercept, which is x equals 5. Our last one is if you cover up the y, you get x equals 12, and you cover up the x, you get y equals 6. So you get these 2 numbers, which on a larger graph you could graph, but in this case we cannot. The only one we could plot is the 6. So how do we graph these, the purple and the green? We'll have to switch it to y equals mx plus b form. Okay? So we do that by, and pardon my penmanship, we would subtract 2x from both sides. So we end up with negative 3y, okay, is less than or equal to negative 2x, and that's a positive 10, so I put plus 10. I like to keep it in mx plus b form because it helps with the visual for graphing. So now you have to divide by negative 3 everywhere. Okay, I'm just going to clone this. So we're dividing each term by negative 3. And when you divide by a negative, okay, this crosses off. When you divide by a negative, the inequality symbol has to flip. So this becomes greater than. These are 2 negatives, which become a positive. So that's 2 divided by 3. And then we have an x. And then 10 divided by negative 3 is negative 3 1/3, but we could just keep it like that. We're not concerned with this number, we're concerned with the slope. So the slope is positive 2 over 3. That means from this point, or any point on that line, again we're dealing with the purple, I'm going to go up 2 and over 3. So I'm going to put my point right here, and that's all I have. I'm going to connect it. And now that it says greater than, I'm going to shade up, shade this way. The red line as well is a greater than, so we're going to shade this way. And notice that this purple equation originally said less than, but because we divided by a negative, it flipped the symbol. This last one is if we were to subtract x from both sides, we'd have 2y is less than or equal to negative x plus 12. Okay, and then if we divide everything by 2, let me divide everything by 2. Okay, and that would leave us with, it looks like a negative 1/2. Okay, this would be a negative 1/2 slope, negative 1/2 slope, and that would be a +6, which look at that, that is our y-intercept already. So we need to go, so down 1 over 2, that's here, down 1 over 2, down 1 over 2, down 1 over 2. So those are connecting. And this 2 says there's no negatives over here. So this is less than, so we're going to go less than. And the last two constraints means it has to be positive x's and positive y's. So our constraints are this weird shaped 1, 2, 3, 4, 5 pentagon. So this whole middle area is the solution area. Okay? And that should be it. This is one last one to try, but this is the solution area.